These photographs may look familiar to you. They're diffraction patterns. At the top here you can see a double slit diffraction pattern where you have lines of maximum and minimum intensity because of the interference of the light waves. Okay, we've got destructive and constructive superposition of the light waves here producing this diffraction pattern. The same is going on down here, except the aperture is different. This is a diffraction pattern from a circular aperture where the light rays have been put through a circular hole. This is a diffraction pattern of light rays that have been put through a triangular hole. A little triangular aperture results in a sort of three-way linear diffraction pattern. This one over here is different though, because this is a diffraction pattern produced with electrons. Now hang on, I hear you cry. Electrons are little particles. They're not waves at all. How can an electron be a wave? But actually in about 1924, a man called Louis de Broglie, who was a French aristocrat, produced a theory that suggested that not only could light behave as a particle, which we now call a photon, but also that matter, i.e. electrons, protons, and even larger lumps of matter can actually behave as waves as it goes through an aperture. And this became known as wave-particle duality. This is the piece of apparatus that's typically used to reveal the wave nature of the electrons. It's called an electron diffraction tube. And let me talk you through this piece of apparatus. Left to right, let's start over here. Here we have a filament, and it's heated by a current, and it's also a cathode. So it's at a low voltage with respect to this piece of the equipment over here, which is the cathode. And in a typical electron diffraction tube, the voltage is around 5,000 volts, about 5 kilovolts. So here, electrons are evaporated off the surface of this metal filament by the process of thermionic emission, and they accelerate up this tube towards the 5 kilovolt anode because they're attracted to its positive potential. When they get here, they're traveling reasonably fast, and then they encounter this. This is a crystal of graphite. So it's layers of carbon atoms in a hexagonal structure. And what happens is some of the electrons will actually pass through the holes between the carbon atoms in the graphite crystal. And when they do that, their behavior changes entirely. Up until this point, they're behaving like little charged particles, accelerating up the tube, attracted to the positive potential, and then here they suddenly start behaving as waves, and they start to diffract through the crystal, through the graphite, and they spread out as they come along, behaving just like waves, and then they hit the screen at the end. And when they do so, you get a pattern that looks like this. Now you can see very distinctly here we have circular bands of light and dark and light and dark, and these are interference fringes, and this is unmistakably a diffraction pattern, which means the electrons must be behaving as waves as they pass through the graphite and through this section of the tube. So how does that occur? Let's have a look at that in a little bit more detail. If you think about the crystal of graphite, it's got lots and lots of layers, and the atoms are arranged at random angles, and so what that creates are little holes in the graphite structure. And so there's one there, that's a rather obvious one right in the middle there. And the spacing between the atoms is approximately 10 to the minus 10 meters. So those are the holes that the electrons pass through. Now if you remember your earlier study in physics, you'll remember that if the size of the aperture, which I'll call d, is roughly equal to the wavelength of the waves, whatever type of waves you've got, that's lambda. So if d is approximately equal to lambda, what you get is very strong diffraction. So what we're saying here is that the wavelength of the electrons must be somewhere in the region of 10 to the minus 10 meters, which is a very, very short wavelength. Okay. Now it gets even stranger because if you increase the accelerating voltage, you will actually speed the electrons up, and the distance between the fringes, i.e. the fringe width, will change. And when the electrons are going faster, the fringes will get closer together. So, I mean, if you think about how that works, we've got energy conservation. All right, we've got the electrical potential energy of the potential difference, which is the charge of the electron multiplied by the voltage that we're applying, 5,000 volts. And that's the work that's done on the electron, which changes its kinetic energy and results in its velocity v. So if you increase v, you can do that by increasing the voltage, but that will actually have an effect on the wavelength lambda. Now if you remember the diffraction equation, we have the aperture width, the slit width if you like, A, and we have the fringe spacing x, and we have the distance to the screen d. Now we're not changing that one or that one. This is changing, alright, and therefore the wavelength itself must be changing. So the wavelength is changing as a simple result of accelerating the electrons to a higher speed, and that's very strange. Okay, so let's have a look at putting all that together. The man in the top right corner of this slide is Louis de Broglie himself. He was the person who came up with the theory. It was actually his PhD thesis, and his examiners were so confused by what he was presenting that they gave the thesis to Einstein to have a look at. So Einstein gave his blessing to de Broglie's work and said, yes, I accept this is perfectly reasonable, this is what's happening with electrons. And so 5 years later, de Broglie won the Nobel Prize for his work. So let's have a look at his equation. On this side we've got the wavelength of the electron, which is sometimes given the subscript dB for de Broglie, so that's the wavelength, and that's equal to h, which, as usual in quantum mechanics, is equal to Planck's constant divided by p, and p is the momentum of the particle, or the electron. Now p is equal to mass times velocity, so that's where the velocity factor comes into it. And sometimes this can be written as h divided by mv for that very reason. So the mass and the velocity affect the wavelength of the particle. If you have a more massive or a faster moving particle, that will mean a shorter wavelength for the electron or the particle that we're talking about. So let's have a go at using that. We have this question here, which we'll do in a second, but if you want to pause the video and have a go at it yourself, then you're very welcome to do so. So an electron is accelerated by a potential difference of 5,000 volts and then diffracted through a crystal. What is the de Broglie wavelength of the electron? Okay, so we're only given one number in this question, and actually there's quite a lot of parts to this question to get to the answer, i.e. the wavelength. So let's have a go. So I'm going to chop this page into two, and over here I'm going to find the velocity of the electron, which is the thing we need to do first, and then I'm going to put it into the de Broglie equation to try and find the wavelength of the particle or the electron. So we're going to use energy conservation first of all. The work done on the electron, i.e. Q times the voltage, electrical potential energy, is equal to the change in kinetic energy of the electron. So what we want is the velocity out of this, because the velocity is what we want to put into the de Broglie equation. So we can rearrange that for velocity, and we get the square root of this 2 that comes up to the top times QV. That's the V for voltage. This is the V for velocity. You've got to be very careful. There are two V's in this equation, divided by the mass. So the velocity will be the square root of 2 times the charge on the electron, which is 1.6 times 10 to the minus 19, multiplied by the voltage, which is 5,000 volts, divided by the mass of the electron itself, which is 9.1 times 10 to the minus 31 kilograms. And when you work all that out, you get a speed of 4.1 times 10 to the 7 meters per second. So the electron's traveling reasonably quickly. Alright, so let's do the second stage. So the de Broglie wavelength is equal to Planck's constant divided by the momentum of the particle, which is equal to mv. So that means 6.63 times 10 to the minus 34, which is Planck's constant, divided by the mass of the electron, 9.1 times 10 to the minus 31, multiplied by its velocity, which is over on the left hand side, 4.1 times 10 to the 7. And when that's all crunched down, you end up with 1.8 times 10 to the minus 11 meters. Alright, so that's the way it's done. So 1.8 times 10 to the minus 11 meters is a typical de Broglie wavelength for electrons. Okay. In what ways is this actually useful? Well, it's very useful actually. This over here is an electron microscope, and certain types of electron microscope, i.e. transmission electron microscopes, where if you have your sample of material that you want to image, you actually send the electrons through that rather than a scanning electron microscope where they reflect off. But a transmission electron microscope, the electrons actually pass through and you will get a diffraction pattern underneath, which you can then analyze to figure out what the structure of your material is. So we're using electrons as waves when we use electron microscopes. In addition to that, we use electrons for another reason. If we just use visible light, we can only get a resolution similar to the wavelength of that, which is a few hundred nanometers. X-rays have a shorter wavelength, so we can get better resolution with X-rays. But if you accelerate electrons with a very large voltage, i.e. 100 kilovolts, you will actually get a wavelength of approximately 10 to the minus 12 meters. And that's the sort of resolution that you can get from your electron microscopes. So, I mean, this is a sample of biological material over here. This line is 100 nanometers long, and you can see within that 100 nanometers there's a lot of detail. So the resolution is extremely good. Much better than you can get with visible light or even with X-rays. We can also probe the structure of matter. We can find out what shape the atomic structure is in different crystals by firing a beam of electrons. If we know the wavelength, we can analyze the diffraction pattern. Effectively the fringe spacing here on this diagram over here, the distance between the maxima, of each spot on the diffraction pattern, and we can figure out what shape the crystal's got. This has probably got a triangular or hexagonal structure to this crystal here.